Hello and welcome back to this 30th lecture of bio microelectromechanical systems. Let's just quickly preview what we did last time. We talked about these famous Navier-Stokes conservation of mass and conservation of momentum equations, tried to derive them from the elementary control volume concept, and then actually try to go ahead and scale down both of these equations and try to figure out how they apply to microfluidics. Let us actually go ahead and just reiterate a little bit of what the conclusions were out of the scaling down. We tried to first take the conservation of momentum equation, and the scaled down version of this equation came out to be dui star by dxi star equals 0, and this essentially indicated, and let me just reiterate that the way that these expressions came into picture, xi would be related to a scaled distance at that particular scale times of xi star, where xi star is a dimensionless number, and similarly ui and uj both were equated to a scaled velocity at that particular scale times of ui star and the same scale velocity times of uj star respectively. Okay, and also we saw that the time star, or the non-dimensional quantity in time in this particular scale, could be represented as the original time divided by the distance by u, the velocity. Okay, and the pressure star, which is again a non-dimensional quantity in pressure in this particular scale, was represented by the term P, which is the absolute value of pressure, divided by neta u by d. As we all know, neta is the viscosity and it's actually scale independent, so it remains constant even if you go to the micron scale. You have to assume though that the equations are that of continuity equations, or the continuum is maintained for the viscosity to be independent of time and a constant property associated with the medium. So because our microflows are mostly in this domain where the continuum is still assumed and all the modeling is done using the continuity equations, therefore it is almost always obvious to assume the viscosity to be constant at that particular scale, and so therefore the pressure star, that means P star, which is essentially the dimensionless number in the Navier-Stokes equation, would be represented as P, the absolute value of the pressure, divided by nu by d. And so we derived the second equation, the conservation of momentum equation, and we figured out that rho u d by eta times of del ui star by del t star plus uj star times of del ui star divided by del xj star would be equal to minus del p star by del xi star plus del 2 ui star divided by or del x with respect to del xj star square, which means that this essentially is the Reynolds number Re, and this we found out last time, the scaling down, and the Re is more or less than 100 in all microfluidic devices, very often less than 0.1. Okay, so it almost always gives you an opportunity to write down minus del p star by del xi star, so the right hand side of this particular equation, plus del 2 ui star divided or del xj star square to be equal to 0, because the left hand side here is essentially dominated by the lesser magnitude of the Reynolds number, and so irrespective of whatever this quantity here is, the overall size of the quantity in the LHS, because of the low value of Reynolds number, is very small in comparison to this quantity inside the brackets. Okay, so because it is overall negligible, we can assume this RHS part of the equation to be equal to 0. So what are our conclusions from this particular statement? So one conclusion which almost always comes out is that at this particular scale the momentum equation becomes time independent. Therefore it is almost always obvious to assume that if suppose you have 2 or 3 flows which are introduced into a same micro channel, and we assume a low value of Reynolds number, due to which the left hand side of this continuity equation or momentum equation becomes 0, the obvious conclusion would be that the pressure driven flow, number 1, and number 2 is that it is time independent. So therefore if you could actually run past both these different types of flows from the outlet end back into the inlet end, or you reverse the flows in time, they should be able to emanate as original inlets to the particular channel. So this is illustrated in this particular example here. If you see, again I would just like to reiterate, and this slide was shown before, that in microfluidics very often there are situations like this here where you are seeing that you have these different dyes which are flowing into this particular channel. You have about 1, 2, 3, 4, 5, 6, 7 different dyes here, okay, and as you see, as this flow happens past this micro channel here and goes for a certain distance, you are able to extract the dyes independent in the same color as they were introduced originally at the other ends. Therefore it is really, the momentum equation is really time independent, okay. Assuming that this were to be true, and this is actually a simulation result done by the Whiteside's group at Harvard, if you assume these flows to be flowing in the reverse direction, then you should be able to get these flows out as independent dyes or as independent colors. So this is in fact the essence of the scale down form of the momentum equation at this particular scale. So the domain of microfluidics therefore is a very novel and interesting domain, wherein it is really very hard for flows laid out together without any diffusional effects to mix. However, because of this particular deliberation that has been just shown in the last slide, and the time independence of the momentum equation, all the mixing which happens at the micron scale takes place because of a concentration gradient, and it is diffusional in nature. So basically that kind of gives us a feel that it may be kind of impossible sometimes to flow two fluids together in a microchannel and mix them if the two flows have equal concentrations and there is no concentration gradient which is established between the flows. That is number 1. And okay, and number 2 is that it becomes a very interesting paradigm in microfluidics to design intelligent systems which could be actually, suppose there is also existence of diffusion in the parallel flow, so which could be actually promoting diffusion and reducing the diffusion time in a manner that it becomes lesser than the residence time of the flows, and the flows start mixing. So these are two interesting paradigms in microfluidics. So I would like to go ahead and actually see some of the effects of Reynolds numbers on the different flows, particularly within microchannels, and I call this slide transition to turbulence within the microchannel. So if you see here, there are different Reynolds number values at which we have plotted the u by u maximum, which is essentially the velocity at a certain position divided by the velocity at the center, which is the maximum velocity, and this is plotted with respect to x by d. X is the position at which the velocity, local velocity, is u, and d is essentially the diameter of the particular channel. So as we see here, the Reynolds number definitely is a very good predictor of when the turbulence will take place. The plot is between the velocity ratio at a point within the microchannel and the ratio of the distance of that point from the center, and the conclusions from this are that if you see this particular plot here, it's basically at a very high Reynolds number value 2770, you see a fairly a large scatter in the velocity. So therefore you can see that if you see this scatter can be also represented by this span of the parabola, okay, and inverted parabola, and so the span is much more in this case as compared to the low Reynolds number cases from 2238 to almost 1980, when the scatter is not that high, okay, and which also shows that probably at 2770 there is a transition or between 2770 and 1980 there is definitely a transition into the turbulent zone. So therefore there is no control really on U after this higher Reynolds number value is reached, whereas at a lower Reynolds number value there is still some control, and you can really say that the flows have not yet turned into eddies or vortices, or it has not really turned into turbulent flows. So that is what this graph would indicate. So therefore the flow shows fairly small scatter between the velocity profiles for RE values between 238 and 1980, and a wide scatter at 2770, which means that the transition is expected in the region 1000 to 2000, which is also true otherwise, that there is a transition definitely between Reynolds number 1000 and 2000, whether it is the macroscopic counterpart or the micro channel. So one more interesting paradigm to be evaluated in microfluidics is related to the effects which can come at the entrance of a micro channel. So as we know that as a channel is approached by a flow of a constant velocity and pressure driven flow, the moment after the flow enters the channel, there is always some time which the flow takes to get fully developed, where this parabolic profile of the flow gets created within the micro channel. Now in cases within channel, in cases of micro channels though, this length which is also known as the entrance length, where the flow profile or whatever the flow profile takes to get developed fully, really also is a kind of function of the Reynolds number, and it is very critical to design microchannels by assuming what really would be the entrance length over and above which the flow is fully developed within the microchannel. So let us explain this event by saying that there are a lot of fundamental differences in the physics of flows between micro and macro scales, and so most of the fabrication techniques as you know are typically 2.5D, and therefore one might think that the flow in 2D is independent of the z direction. However, the aspect ratios that are normally realized as sometimes 1 and z becomes a critical direction, okay, for these kind of flows. And when a fluid flows from a large vessel or a reservoir into a small one of a constant cross section, which means that the velocity of approach of this particular flow is almost constant as it approaches this small channel here, the flow takes, or the flow profile requires a certain distance to get fully developed, okay. So this is also known as the entrance length. So various people have tried to experimentally and otherwise calculate what this entrance length would be, and so the best experiment that was proposed by Shaw in London was that the amount of length needed for center line velocity to develop 95% of the full velocity is actually given by this expression here. LE is the entrance length divided by DH is equal to, so DH is essentially the diameter of the particular channel, is equal to 0.6 divided by 0.035 RE Reynolds number at that particular diameter or cross section, and plus 0.056 RE Reynolds number at that particular cross section, okay. So entrance length really is then a function of the Reynolds number very critically, and also the cross sectional diameter of the particular micro channel. So typically LE is normally about 60% of the hydraulic diameter in case the Reynolds number is low, because then there is the one is prominent over this term 0.035 Reynolds number or 0.056 Reynolds number. But however, in cases where this Reynolds number becomes a little bigger, the entrance length effects are felt more appropriately. This is the hydraulic diameter, okay, cross sectional diameter of the hydraulic diameter. So so in cases where the Reynolds number becomes a little bigger, and the contribution from this term and this term is significantly enhanced, and therefore the entrance length becomes less than 60%, okay, of the hydraulic diameter. what does it mean really? It means that if suppose in case of a micro channel, when the Reynolds number is comparatively low, the entrance length has significant amount in terms of 60% of the hydraulic diameter, as opposed to macro scale where the Re is more, where this is much lesser than 60%. So this kind of shows that whenever you want to design micro channel, you almost have to be careful always about selecting the entrance length before the perturbations or structures that you would like to create within the micro channels to cause certain phenomena, physical phenomena, would start to be placed. So you need to wait up till the entrance, the whole entrance length which is needed for developing the flow fully is traversed before the flow can get into a region where significant differences can be made to it by changing the physical form or shape of the micro channel. So definitely entrance effects are very critical as far as microfluidics are concerned. So this kind of brings us to an end of the kind of theoretical analysis that was needed to understand microfluidics. So I would like to go ahead now today and try to get into a little more different area as to what would happen really if the continuum assumptions fail, and essentially then would be talking about things which are more related to intermolecular forces, and scaling from microns to nanometers. It is very important that we consider now an altogether different approach, which is not driven by continuity, okay, and which is more driven by intermolecular forces between the molecules which are present in a very small nanometer cube size, probably control volume, okay. And after that, after looking into that aspect, really I would like to go ahead and start the topics of the actual technology that microfluidics can be put to and then can be directly applied to, as in biomems, wherein we would start realizing these active devices like microvalves, micromixers, micropumps, etc. And the idea is that after we demonstrate all these on a fundamental level, we will go ahead and assemble these units together on a single biomems platform, which would do something useful and important. So the last parts of the course would be probably dedicated to reviewing some of the papers and articles which have been in this area, where these small fundamental concepts are introduced and integrated together to form integrated systems, which would do total chemical analysis. So let's actually go ahead and see what happens when the scale changes to a little bit lower. And as I told you before in one of my earlier lectures, that continuum assumptions fail beyond a certain scale. Let's say, for example, if you have a small control volume which is about 1 nanometer cube in dimensions, and you assume or you try to find out what is the density or velocity of molecules which are within this 1 nanometer cube. So there is a tendency of the molecules to rush past the boundaries of these very randomly with time, as a resulting in a change in density with time, maybe a change in viscosity with time. So all these properties which were assumed to be kind of averaged out properties, as in case of continuum mechanics or continuum fluid mechanics, would actually boil down to a time dependent property when you go to this particular scale. And so therefore whatever presumptions Navier-Stokes equations made in assuming that okay, the density is constant, the flow is incompressible, or even if the velocity or this really only dependent on space, and even if it is dependent on time, it does not change at a certain instant of time. So these assumptions were made in order to derive the Navier-Stokes equations. However, that is not true at that small scale of 1 nanometer cube or so, and so therefore intermolecular forces would play a major role there in order to figure out what is going on in terms of interactions between the molecules, etc. Okay, so intermolecular forces. So what are intermolecular forces really? So if you look at the different states of matter, you can really categorize matter into solids, liquids and gases, okay, and these are all based on the interaction among the different states depending on the forces between molecules of these particular states, okay, which comprise the matter. So, these interaction forces can be very well explained by a model of potential energy of two such molecular systems which are close by a distance r, okay. And this is also known as the Lennard-Jones potential model. Essentially it is a non-dimensional equation, and we have a scaled down factor there. So, you have a scale factor for distance essentially between, let us say, two molecular systems. And so, without going into the details of derivation of such an equation, I would just like to illustrate, because most of the simulation work which is at this nanometric scale, when as far as fluidics is concerned, is more using this model of Lennard-Jones potential. So, let us say you have two systems I and J, and that means there are two molecular systems of this particular notation, and they are separated by a distance r, okay. So, the potential that would happen between two of these I and J systems is essentially equal to 4 epsilon Cij r by sigma to the power minus 12 minus Dij r by sigma to the power of minus 6. Let me just go ahead and explain what all these different terms are. So, epsilon is essentially the scaled energy, okay. Now, this is the scaled energy, the characteristic energy scale we call it, characteristic energy scale, and sigma is the characteristic distance scale or the length scale, okay. So, this is the length scale. By now you are probably familiar, because we did a scaling down in the Navier-Stokes equation of conservation of momentum. You probably are aware of what these different scales mean. So, it is essentially a characteristic distance or a characteristic energy value at the scale at which all these different forces or potentials are considered, okay. So, r by sigma essentially is a non-dimensional term. Similarly, Vij by epsilon again is a non-dimensional term, because it is a comparison of the potential with respect to an energy scale. That means a value of energy at that particular scale in which all these experiments or all this equation is being used for studying the intermolecular behavior, okay. What is more interesting here is that there are two different terms and dependencies on r by sigma. One is to the power of minus 12, another is to the power of minus 6. So, these essentially this minus 12 term would signify the pairwise repulsion, okay, that exists between two molecules, and these repulsions, as you all know, are because of inter-electronic repulsions between the two molecular systems. So, there are orbitals which contain electrons, or which has a probability of having an electron or having a bunch of electrons, and when two of such molecular systems come close by, there is a repulsion between the electrons on both these systems, which would cause them to have a positive potential, okay. So, it takes some work for getting them any closer than the characteristic distance r in which they are placed, okay. So, that is what the r minus 12 dependence would signify, and then there is a r minus 6 dependence which is a mildly attractive potential, and this is due to van der Waals interaction forces. So, what are really van der Waals forces? They are basically attractions formulated between two such molecular systems, between the electrons on one and the nucleus on another, and similarly the electrons on the other and the nucleus on the first one. So, that is what van der Waals interaction forces are, and they are principally attractive in nature. However, they are very weak forces, because essentially the attraction between the nucleus on the first and the electron on the second has to go through an electronic layer. I mean, it has to shield through an electronic layer, it is shielded by an electronic layer which is in between. So, therefore, the r by sigma to the power minus 6 dependency is pretty much a weak force in comparison to the minus 12 dependency, which is a strong force. So, therefore, we can easily say that the potential is contributed by the pairwise repulsion and the pairwise attraction given by these two terms here, minus 12 and minus 6. Also what is interesting for me to tell you is that as you know, force of in between these two systems I and j is also represented by a negative gradient of the potential between the two systems. So we can calculate Fij, the force, as minus dVij by dr, where r is the intermolecular distance between these two molecular systems. So Fijr essentially is minus dVijr by dr, and if I actually differentiate this Vij term here with respect to r, we get 46 epsilon by sigma Cij r by sigma to the power of minus 13, which is the pairwise repulsion force probably, and minus Dij by 2 r by sigma to the power of minus 7, which is the pairwise van der Waals attraction force. Now so in this particular scale I can also assume that the corresponding time scale would be represented by this quantity here, sigma root over m by epsilon. M by epsilon again is mass per unit energy, which has the dimensions of square of velocity, okay. And so a typical characteristic velocity at this scale could be represented by the mass at this scale divided by the energy at this particular scale. And so therefore if you underroot the mass per unit energy, it gives you the velocity scale, and dividing the distance sigma by the velocity scale would give you an indication of the time scale, what kind of times or characteristic times would exist in this particular scale. So what is also interesting here is that if you really plot the dimensionless parameters Vr by 4 epsilon and Fr by 48 epsilon times sigma, which is essentially, if you just see back in this equation, nothing but this whole dimensional term in one case, the force divided by 48 epsilon sigma, and this whole dimensional term on another case which is Vij, the potential function, divided by 4 epsilon. So these are two non-dimensional terms, and what is interesting here to find out is that essentially there are two curves which come out. One is for the potential function, okay, and of course these dimensionless numbers are plotted by the with respect to the separation distance r by sigma. So what we find out here is that the behavior in both the cases, okay, are pretty much similar, except the fact that the force value has a more deeper well in comparison to the potential value has a much more deeper well in comparison to the force value here, okay. What is also interesting here is to note that beyond a certain distance, let us say this particular distance where it really has the peak point, okay, the forces kind of try to gain prominence of the van der Waals attraction. So this region here is the repulsive force. So if you see the dimensionless quantity in this particular example, Fr sigma by 48 E is continuously going down, which means that if you look at the dimensional quantity here, which is, let us say, Cij r by sigma to the power of minus 13 minus Dij by 2 r by sigma to the power of minus 7. So this going down would signify that this term here, the second term here, is starting to dominate, and which means that, you know, this is the pairwise repulsion, this is the pairwise attraction, the van der Waals attraction. So the van der Waals attraction is continuously dominating, or it's trying to dominate, but essentially it is being superposed by the higher value of r by sigma when it is below a certain separation distance. So after it crosses a certain characteristic separation distance, this component here really predominates, okay, which is actually essentially this point here, okay, where the pairwise attraction becomes more than the pairwise repulsion, after which again there is a slow prominence or a slow gain of the first term where it asymptotically goes all the way to 0. So if you draw the potential function, really it also shows similar behavior, and the point where the forces have really changed from being perfectly repulsive to slightly attractive here, the potential function is actually dipping down to its minima, okay, at that particular point, where there probably close to zero forces. There are no forces of any attraction or repulsion, and the attraction repulsion has kind of balanced each other. Both the terms in the dimensionless quantity are equal to each other. Okay. So if you really look at these Reynolds, this Lennard-Jones functions in case of diatomic gases particularly, or in case of certain gaseous states, the values of various parameters available are for a limited number of molecules have only been studied and summarized. Okay. And especially they have been done so more for gases, wherein you can find out the characteristic energy scale per unit Boltzmann constant and also the characteristic distance scale. Mind you, there are only very few systems in the world which have been really modeled and studied for finding out these different energy scales or distance scales, etc. Some of them are illustrated here in the table, like for example in case of air, the energy scale would be typically energy scale per unit Boltzmann constant K would typically be equal to about 97 Kelvin. For N2 nitrogen it would be about 91.5, for CO2 it is 190, oxygen it is 113, AR 124, so on and so forth. And in terms of distance scale in nanometer range, air molecules have probably a characteristic distance of 0.362, which goes all the way to about 0.342 for argon. These have been of course calculated or assumed by assuming the Cij and Cij and Dij parameters to be both unity. That is how these values have been really calculated. So the time scale for these kind of energy and distance scales come out to be about 2.2 picoseconds. Okay. So these are some of the characteristic dimensions which are available at the atomistic scale that we are talking about. The plot again here, as you are seeing, has been shown only for these few systems. What is interesting here, what I did not discuss before, is that it is basically the potential energy scaled by a factor of 1 by 4 epsilon and the force scaled by sigma by 4 epsilon. And so the effects of these constants in the table above here really is to not change the basic characteristic, but to actually shift it by adding a DC bias. So the whole curve can shift up and down if these characteristic parameters epsilon by k and sigma would change without really changing the behavior or the trend that the dimensionless number would follow with respect to r by sigma. Okay. So that is all about Lennard-Jones potential models. Okay. So if you look at the states of matters really, what are the differences in terms of forces. So in a solid we can assume all the molecules being densely packed and held by strong repulsive forces. This pairwise repulsion is very high in some solids, and as a result of which putting a particular atom from its position out of that is highly difficult, because it is being repelled from all these sides by equal amount of high repulsive forces. So it remains in its state very firmly bound in where it is without really being able to get liberated from that particular state. So moving an atom from one neighborhood to another becomes an immense problem. So for a molecule to kind of leave its neighborhood and join another neighborhood, you would need to provide energy to the system, and this energy would be in terms of thermal energy. So essentially if you have bond vibrations which are happening between these molecular system, after a while the kinetic energy of the molecules would be sufficient enough for it to leave one neighborhood to another, and that is also known as the melting temperature or the melting point of the particular solid, where the molecules are just about capable to move between neighborhoods, and it has sufficient amount of kinetic energy for doing that. And beyond the melting temperature, of course, the average molecular thermal energy becomes high enough so that the molecules are able to vibrate freely, go over large distances, and between one neighborhood to another, and if the distance that they are traversing or the distance scale that they are traversing is still sigma, they are also called liquid state material. Okay. But then if the distance becomes almost an order of magnitude more, like about 10 sigma or so, they are known as gaseous states. In that kind of a situation where the intermolecular distance is more than about 10 sigma, sigma being the distance scale in the solid state, these are essentially then known as the boiling temperature, and the species are known as gaseous species. So in a nutshell, there are 3 different configurations to look at. Solid state, the atoms are firmly bound, there are huge amount of repulsive forces to an atom in its pocket from all its neighbors, and movement between neighborhoods becomes an impossibility. In gaseous state or in a liquid state, just about when kinetic energy is applied has been able to lift it to a state where the atom can move from one neighborhood to another. However, the distances moved is still about same range sigma, but the movement just becomes possible. It is known as the liquid state, or the melting point of the material, and at a point when this sigma increases to about 10 sigma or so, and there is total decontrol on the molecule from its current location, it reaches the boiling point. It is known as a gas phase. So therefore, with this kind of a concept in mind, let us actually look at what happens when the continuum fails. Okay, so we would like to do this molecular approaches to estimate flows, particularly when there is a failure of the continuum approach. And so the only other approach which has probably emerged for solving liquid flows is called molecular dynamic simulations, which talks about all these intermolecular forces, as I have been telling before, intermolecular forces, and which can be established from the Lennard-Jones potential model. Okay. So the MD technique is in principle very straightforward. It is an application of just Newton's second law. Okay, and so what is Newton's second law? The product of mass and acceleration is equal to the total amount of force that a particular system should have. So same can be translated into molecular systems as well. So however, we have to somehow ascertain how to find the acceleration of this kind of a molecular system, and we already know that from Lennard-Jones potential we can find out the average force between two molecular systems I and G separated by a distance of r. Okay, so essentially that is what we are doing here. The product of mass and acceleration of each particle is equated to the sum total of forces because of Lennard-Jones equations, and the technique really begins with a collection of molecules in space. Now each molecule has a random velocity assigned to it as per Boltzmann velocity distribution, and the molecular velocities are integrated forward in time to arrive at the new molecular positions. Okay, and if you see the intermolecular forces really which are equated to mi d2 ri by dt2 at time t, let us say time instant t, is equal to minus d by dr, this is the negative gradient of potential, Lennard-Jones potential, sigma I not equal to j, that means these are systems, all systems of the likes I and all systems of the likes j, they are two different molecular systems between which there is a force of attraction and repulsion. So it is the negative gradient with respect to r of Vij, and here the assumptions that we use to simplify is that if you consider a molecular system, really it is a huge amount or a huge number of molecules. 1 mole, as you know, is about 10 to the power of 23 molecules. Okay, and so therefore if suppose you are talking about a certain radius, or if you are talking about a molecular system where there are thousands of these molecules which are interplaying, and there are intermolecular forces between these thousands of molecules, there would be a tendency of the computations to go extensively at a very high rate. Okay, and that is sometimes, so essentially the whole idea is that, you know, in a molecular system like this, if you have one molecule and surrounding thousands or actually millions of molecules, there are intermolecular forces between this one molecule of interest and its neighborhood, which comprises of millions of such forces, and you know, it makes the whole system computationally extensive, and the solutions may not converge with time, and there may be issues related to more number of computations. And so to solve this problem, you really need to consider an effective radius within which you can consider the interactions. So this is called a cutoff radius, and if the radius is exceeded or the radius goes beyond the cutoff radius, we assume that the molecular forces arising out of molecules arising or which are outside this cutoff radius is 0. Okay. So you kind of terminate the calculations at a certain intermolecular distance, beyond which you assume that the distances are too large for the forces to be really effective in the overall calculations. So therefore this Lennard-Jones function really changes into Vij Ri minus Rj vectors. Rj is essentially the vector radius where there would be a force cutoff. Okay. So this is the cutting radius or cutoff radius, and any point below this would be effectively considered in the calculations here. So the force, so it is kind of a truncated solution. So the truncated solution of the force between a radius with a cutoff radius of, let us say, Rj in this particular case, is given by minus dy dr of sigma I not equal to j. That means these are two different molecular systems, Vij Ri minus Rj mod. Okay. And this is equated to by the Newton's second law Mi del 2 Ri vector by dt2. So this is the acceleration at time t, and the forward integration of this twice successively would give you the new position vector Ri, from which you could again recalculate this, consider its a criteria to define the new cutoff radius, and so therefore from position to position you can have a very good estimate of the velocity, the position vectors and the acceleration vectors of these individual particles based on this force change of momentum approximation. And so therefore the averages of velocities, let us say, are calculated by, if you have knowledge of all positions by this forward time integration and you want to find the x velocity. So all the x positions, you know the d by dxi by dt, you make a sigma of all these and calculate an average velocity, an average density, an average of other properties, etc. Now mind you, because these positions are changing with time, these quantities would also be changing with time. So even though the continuum assumption is not validated in this particular case, the averages keep on varying based on the interactions, the molecular interactions in that small control volume. And so therefore this is a very appropriate and a very accurate technique to simulate the motion or properties of fluids at the nanometer scale. So these are called molecular dynamic simulations. In fact, such simulations can be used to study a lot of properties like combustion, fluid mechanics in general, then all sort of surface based interactions with charged molecules or interactions between different charged molecules in a system, so on and so forth, and they are very, very useful as a technique to predict the position vectors, velocity, average properties, etc., time variant essentially. So this kind of gives you an estimate of how from continuum to a scale where continuum does not hold, you could change your approach to get different solutions. Now I would like to now go more towards the application side and describe these different kind of applications of these micro scale fluidic techniques into realizing engineering products like micro valves, micro mixers, micro pumps, etc. So let us study these one by one. So would like to first start by looking at micro mixers. Okay. So if you look at really the characterization of microflows, the first property which comes out, as we have seen earlier, is the low value of Reynolds number. Of course is the ratio between inertial and viscous forces again, and you can mathematically define it as rho Vd by mu. Rho is the density, V is the velocity, d is the dimension at that particular scale, and mu is the viscosity of the medium. Okay, and the way you calculate d in Reynolds number is essentially 4 times area by parameter, and is also known as the hydraulic diameter of a particular section. So based on the different ranges that this Reynolds number kind of comes into, ranges of values, you could categorize flows into many types. Okay, so this table here illustrates the corresponding range of Reynolds number with the description of the flow. So as you are looking at Re between 0 and 1, which is mostly the case in microfluidics, the flows are highly viscous, they are highly laminar, and they are as if they execute creeping motion, as if they are moving in a very tightly packed, close packed channel, or creeping in a close packed channel without really interfering much into each other's path. The molecules move in perfect streamlines parallel to each other. So for a Reynolds number of 1 to 100, the flows still remain very laminar, and there is of course a very strong dependency on the Reynolds number at this particular scale. So suddenly the flow properties may demonstrate a change in behavior with a very minute change in the Reynolds number. If you go slightly above and consider the Reynolds number between 100 and 1000, the flows again are very laminar, they have not yet changed regimes. However, here in this particular range you could really have a very good boundary layer which is formulated. If you may recall, boundary layer again is the layer which is separating the fully developed flow from the flow which is made up of the flow which is actually having shear stress. Okay, or they are predominated by shear. So therefore this boundary between the fully developed part and the sheared part of the flow is what laminar boundary layer apparently is, and this boundary layer formulates whenever very close to a fixed surface, maybe a channel inner, or some kind of a flat plate or flow over a surface. So essentially this Reynolds number range of 100 to 1000 would inculcate a prominent boundary layer, and here most of the theorizing of boundary layer is very useful. If you change the Reynolds number a little bit from 1000 plus all the way to about 10,000, there is a slow transition which takes place. The flow goes from laminar to turbulence, but then this is really a transition. You have instances where the flow is slightly laminar, or instances where the flow is turbulent, and there is slowly changing the behavior. Okay, after a certain value, let us say 10 to the power 4 or so, and up to about 10 to the power 6, the flow becomes fully turbulent. Okay, and of course in this particular range there is some Reynolds number dependence which happens, particularly from 10 to the power 4 to 10 to the power 5 Reynolds number, beyond which up to all the way up to infinity, not only flow is turbulent, but it is having any very less dependency on the Reynolds number, and essentially that is probably because the flow really gets defined by the local eddies and vortices more than the overall bulk flow, and that is essentially what these different categories of flows are with respect to different values of Reynolds numbers. So what I would like to reiterate here is that as I told you before, in the 1 to 100 case, or even less than 1 case, as is mostly the case in all the microfluidic devices, the mixing behavior or the mass transport between the mixing interlayers typically is not really dependent on the momentum, okay, of the flows. There are no eddies or no vortices which would cause mass transport between the two mixing interlayers just by virtue of motion. You need something else to drive the flow in a perpendicular direction, and what could be more appropriate than a concentration gradient, and so therefore the diffusion approximation comes into picture. Most of the micro scale flows mixing takes place primarily by diffusion, and if you look at the diffusion equations, really the diffusion flux, because of the existence of this concentration gradient here dC by dx, okay, they are kind of proportional to each other. So diffusion flux is proportional to the negative gradient of concentration with respect to the perpendicular distance. And the proportionality constant really is d here, the diffusion constant, which can be varied for different states of the matter. For example, diffusion constant is very low if you consider solid. You see the scale below here, diffusion constant is in the range of about 10 to the power minus 10 in case of solids. In case of polymers and glasses, this constant increases a little bit, goes to about 10 to the power minus 8, but still is very low. Most liquids have a diffusion constant in the range of 10 to the power minus 6 to minus 4 in this particular region, and so therefore it is of some significance, the diffusion is of some significance as far as liquid is concerned. But in case of gases, this constant is very high, it is about 10 to the power minus 2 to 1 centimeter square per second, and so therefore you have to be very careful about diffusion as you go to gas flows. However, most microfluidics being single phase and mostly liquid dominated, the diffusion constants that we will be considering in all our calculations are in the range of about 10 to the power minus 6 to minus 4. Okay. So the mass transport mt across the boundary between two fluids is also equal to the flux times of the area of interface between the two mixing fluids. So you have, let us say, two fluids running parallel and their interfacial area is A and flux is phi. So the amount of mass transport mt really is equal to phi times A, phi being the mass transport per unit area, or the flux of mass per unit area. So therefore interfacial area in such cases becomes highly prominent, especially when mixing is concerned. So if you have somehow a mechanism wherein you can accommodate two flows over a longer amount of or over a larger amount of area, automatically their mass transport would be more. Sometimes it becomes architecturally promising to design micromixers where this area of interface between the two flows is increased, resulting in some mass transport. Okay. So if area is more, then the mass transport mt is more. Also of special significance is an equation which I am not going to prove here though, but then I have just borrowed it from normal diffusion kinetics, and here it talks about the time of diffusion. And so the time of diffusion is essentially equal to d square by 2d, d being the path length over which the two flows are going, for which they are diffusing at the end or throughout as they are going with respect to each other, and big D here is the diffusion coefficient. Okay. So if you have a length L of a channel over which these two flows are mixing and going as they move along, the length L is nothing but the path L, okay, the path D, a path length D. So if the length is more, then in that case the time of diffusion tau is automatically more. So this length is essentially the cross sectional length when we are talking about two flows which are going in a particular channel of the cross sectional length L. Okay. So it almost makes sense to assume here that the time of diffusion will reduce if the d value, that is the cross sectional length value of the two flows, is reduced. Okay. So if I am able to somehow create shorter laminae of these flows, and thus the cross sectional length of the flow reduces by division of d into, let us say, n, where n is the number of laminae, then automatically the time of diffusion should also reduce as the square of the reduction in the d. And it is very important understanding that one must have in order to design what you call passive micromixers, where the whole idea is how the diffusion length can be split up into smaller values so that time of diffusion would reduce. And the whole essence of microfluidic structures or microfluidic architectures is how the time where these two flows have been introduced from one side and reside within the chip is going to be more than the time that the fluids take to diffuse into each other. So by the end of the day, at the end of the day, when it emerges out from the other side of the chip, they are fully mixed. Okay. So range of d values for different states are indicated here in this particular illustration, and
Essentially that is a little bit of fundamentals of how mixing would take place at the microscopic length scale. So what really would be considered when we talk about design of micro mixers. So the number one problem that we are left with is the small value of the Reynolds number and therefore the diffusive mixing. So design considerations should be definitely based on somehow being able to promote a diffusion between the two layers, and essentially which means faster mixing time, okay, general requirements, small device size, and also you should have kind of integration ability particularly in complex systems with the overall setup, okay. So fast mixing time again can be achieved by, as I told you before, decreasing the path length, okay. The path length means the cross sectional path, the path that diffusion happens along is perpendicular to the direction of the actual flow of these fluids, okay. And you can also have more accurate or better mixing and faster mixing by increasing the interfacial area between the two or more mixing streams. So smaller the mixing channel length, faster would be the mixing process, okay. However, the desired high throughput, particulate in field and high driving pressures do not tolerate too small channels. That is the unfortunate part. Most of these flows in microfluidics, as you know, are pressure driven, and therefore too small a channel would have too high a resistance, and therefore the yield at the end of the channel of the flow would be so small that it is very negligible. So you have to design something wherein you can still be able to get substantial amount of throughput, but at the same time the mixing can be faster, and so therefore lamination is something that comes into picture automatically. That means you split up let us say two streams of two different dyes or two different colors which you want to mix into multiple streams stacking with each other. So if you have n such splits, what would happen is that you have one stream with a diffusion length d, a cross sectional length, or two streams going into a cross sectional length L or d, which is also the diffusion length, and in another instance after n splitting the cross section length is simply reduced by d by n. We are going to investigate this a little bit further as we do mixer designing. So therefore the first solution really is to split n substreams and rejoining them again in a single stream, so that the mixing time reduces by a factor of n square. So this is basically the principle of lamination mixers. So this kind of brings us to an end of this particular lecture. We have a take home message that mixing essentially is diffusional, it is dependent on the interfacial area, it is dependent on the diffusion length. Time of diffusion essentially has to be kind of lesser than the time of residence for the flow to be effectively mixing with each other, and overall requirements of a micromixer should be it has a faster mixing time, small device size and integration ability, particularly in a higher order complex system, okay. So we will consider these aspects in a little more detail in the next lecture. Thank you.